to the Future of Function Global Sake Global SF. This is our very first virtual event for Global Sake, so bear with us and welcome everyone. Very exciting to have you here. I'm Talia Baruch, I'm the co-founder of Global Sake. We're a collective community of leads around the world driving international new markets growth. Our mission is to simply bring people together across functions, cultures, borders, bringing the diverse perspectives and the complementing skill sets to solve big global problems. Please join our Global Sake LinkedIn group to meet other peers for collaborations, for knowledge share. We run annual conferences like this one, always typically physical, and you're in for a great treat tonight, or today for the rest day. Enjoy.
Thank you so much, Talia. I'm Laura Jenkins. I'm the Director of Partnerships for Global SF and thrilled to partner with Global Sake for the Future of Function today. Global SF is a nonprofit and it's a public-private partnership with the City of San Francisco. And we work to support economic relations and build partnerships at the global level. So we partner with the state of California as well and help entrepreneurs, companies, funds, investment from around the world expanding to the Bay Area. And we also help companies already based in the Bay Area to expand globally by making introductions and connections to the right partners. So I can't wait to learn from the speakers here today, representing such diverse perspectives, industries, and locations about these new opportunities now and ways of thinking and strategies for finding solutions in this new reality across geographies. So thank you so much, and I can't wait to start this adventure all day long.
All right, good morning, everybody. My name is John Hatto-Brandenhorst. I am one of the co-founders of Global Sake. Excited for a great day of talks. In an in-person event, this would be more of a build-up, but just wanted to say welcome. Wanted to say thank you to our wonderful sponsors. We have Alpha in the house, Jetro, Morrison & Forrester, Intento, Morgan Lewis, and Plexor, Wix, Women in Localization, Gala, Level 3, and Paday & Company. So we are going to be going right on time with everything today, and to give our kickoff speaker as much time as possible, I'd like to welcome Brady Bruce, who will be talking about the automated factory of the future. So without further ado, I'd like to welcome Brady. And I will stop sharing. And Brady, feel free to take over the screen.
Thanks, John. Let me just share my screen here and we'll get started. Good, you should be able to see my screen now, I hope. Good morning, I'm Brady Bruce and I head up marketing at Tempo Automation. Today I'd like to talk about the future of manufacturing and how manufacturing is itself the act of materializing data. We're an innovative species. We imagine and we create from that imagination. We express ourselves by manifesting in the real world the things we develop in our interior world. We convert the potential to the actual. We write, we tell stories, we paint and sculpt, we build, we invent technologies to address our needs and ambitions. In the case of art or artisanal goods, the artist or artisan has an idea and then creates it. The step from ideation to creation is a singular one. It's a deeply human process and it works well. In the case of complex technologies, well, it gets more complex. More people are involved, more processes and systems are engaged. In the ideal version, the engineer has an idea, renders it in a form that can be shared with all of the people and processes and machines that will build the product. In the ideal version, everyone sees the same information and understands it in exactly the same way. That process works best if it begins with unambiguous information about every aspect of the thing to be built, and if that unambiguous information is received and perfectly understood. It may surprise you to hear that that's not the way most new technologies are brought to market. In fact, there's a lot that can and does go wrong between the design and the launch of a new technology. The process that works so well for art is not well adapted for bringing new technologies to life. Distorted information, lost data, misinterpretation, misunderstanding, failures in communication, fatigue, changes in personnel, it all gets in the way of the perfect expression of the original idea. The results are products that don't precisely match the design or the designer's intent. The costs of that failure are measured in lost time, missed opportunities, disappointed customers, and exploding development budgets. While this is true of all types of hardware technology launches, today we're going to talk about the particular case of electronics, specifically the printed circuit boards, or PCBs. PCBs are at the heart of most of the devices in your life. The laptop or the mobile phone you're watching this webinar on, the satellites and broadband infrastructure that are delivering the signal to you, the car or transit system you use, the medical devices your doctors employ, and the aircraft we all hope to fly on again someday. Almost everything that plugs into power or uses a battery, look inside and you'll find a printed circuit board. Some are tiny enough to fit into a hearing aid. Others would barely fit into your backpack. So, how do designs become new products? Prototyping. Very few ideas become great products without prototyping. And it's worth looking into the black box of processes that are deployed to move from an innovative design to a new product in the world. I should note here that while some very large companies do their own prototype manufacturing, most use contract manufacturers, or CMs, to do the work. In the world of electronics, these are the typical processes involved in creating prototypes. Traditionally, these are labor intensive and involve lots of people examining and passing along information, and often doing so imperfectly. Starting at the top of the list, design ingestion describes the handoff of the design from the designer to the CM who will build the prototype. DFM stands for the design for manufacturing study that a CM will do. It works this way. Experts at the typical CM will spend many hours or days poring over the design to see if it can actually be built as specified, or if that design needs to be altered to eliminate any impossibilities or obvious faults. At this point, the CM provides feedback to the designer in order to resolve any manufacturability issues. And this communication typically takes the form of a lot of phone calls or emails. Once everyone's agreed on the build plan, the CM begins the work of materials sourcing, combing through catalogs of parts suppliers, and then placing orders for those parts. Once the parts have all arrived at the factory, people get to the work of factory programming. This typically involves a few hours of people sitting at a screen attached to each of the machines in the factory and giving them instructions for the next product to be built. Things like what kinds of solder to use, where to place hundreds of components, the right temperatures, and so on. And finally, after all of those machines have been programmed individually, manufacturing begins. The prototypes are built, and then they're shipped back to the designer who plugs them into a test system to see if they perform as intended. If not, changes are made to the design and the next batch of prototypes are built. And this is repeated over and over again until the designer is satisfied that the product performs as hoped. It's common for complex electronics to go through 6 or 7 or more iterations of prototyping. Now, there is data at the center here but it's subject to corruption and miscommunication that's inherent in the old manual way of doing things. And any mistake made in any of these steps or in the handoffs between them propagates through the entire process. So, how can prototyping be improved to speed time to market with better results? My company, Tempo Automation, develops software that automates, manages, and makes prototyping better. In fact, we're a software company that also runs an electronics factory that's unlike any other. We're a contract manufacturer. Our smart factory in downtown San Francisco builds prototype printed circuit boards for some of the biggest, most successful technology companies on earth, as well as for many ambitious startups. They send rockets to space, they explore the deepest parts of the ocean, they build autonomous vehicles, they make industrial robots, they deliver life-saving medical diagnostics and therapeutics. We help them get from concept to finished product faster and better than has ever been possible before. Some of them will build 10 prototypes at a time, some will build 100, and for some of them, we build more than their prototypes. For those who make products like satellites and advanced medical imaging systems that are built in quantities less than 1,000, we also build the electronics that go into their go-to-market products. Now, our customers value their privacy, but there are a few names I have permission to drop here. NASA, GE Healthcare, Lockheed Martin, Berkshire Grey, Spire, to name a few. So, what is it that makes a smart factory smart? It starts with data. In other factories, the process starts with drawings and notes from the designer, because that's how they've done it for 50 years and that's all they're equipped to work with. That analog format that most other CMs use, the Gerber file, is commonly referred to by its own users as art. And that should tell you all you need to know. Using Gerber files requires that the contract manufacturer ask a lot of questions of the designer, typically more rounds of phone calls and communications, with gathered information being passed among a lot of people. Interpretation is a big part of that method. The deconstructions and reconstructions of those interpretations create opportunities for corruption of the original design and does not capture the design intent. We took a different approach. We built software to ingest design data directly. Our customers submit their original native digital design files. Those contain deep information about the design, how the design was created, what purpose the product is intended to serve, and how it's intended to perform. That data is unambiguous. It does not need to be interpreted. It represents perfectly the design and the designer's intent. Once our software receives the digital design, it performs feature extraction. Now, feature extraction captures all of the information describing the design and the designer's intent, and it builds a functional model of the board and its circuitry. The customer also provides us with the list of all the components they want used on the board, the bill of materials, or BOM. Our software reads that BOM and begins placing orders for the components from our network of trusted partners whose databases we've plumbed. Our system probabilistically looks for the best prices and looks at history to determine which distributor is most likely to have that part delivered to us first. All of that information becomes the single source of truth and the central stream of data that will accompany the job all the way through our factory. We call it the digital thread. Next, our software creates a photorealistic fabrication simulation that shows exactly what the board will look like when it's built. On the screen before you, you see two images. One of those is the fab sim. The other is an actual photo of the finished board. I suspect you can't tell the difference. Most people can't, even on close inspection. That fab sim joins the feature extraction in the digital thread. And the fab sim serves another essential purpose: quality assurance, or QA. In other factories, QA is handled in a very different way. The manufacturer first runs through the factory a single board based on their best interpretation of the design. They spend hours poring over it to make sure that that artifact accurately reflects the design that was submitted. And they call that artifact the gold master. And they will then compare every other board that comes off the production line to it. If a board matches the gold master exactly, it's good. If it deviates in any way, it's bad. Here's the problem. The gold master is the end product of a process that relies on analog data, imperfect communication, and interpretation. Any problem in that gold master will now be repeated in every other board that matches it perfectly. It's designed to work that way. At Tempo, we use the fab sim, the ideal representation of the original design and the designer's intent, to do QA. At the end of the production line, all of the boards we make are put into an automated optical inspection robot. It has a very powerful camera that moves on an XY gantry very quickly, looking at the critical parts of the finished boards, comparing them not to a gold master that may or may not be perfect, but instead comparing them to the fab sim that's embedded in the digital thread. I called our factory a smart factory. The first characteristic of a smart factory is that it's driven by unambiguous data. The second is that it learns with each successive order. This fab sim benefits from everything our system has learned about material properties and machine tolerances and other parameters that are central to the manufacturing process. By the way, that fab sim is also directly useful to our customers. We share it with them at the beginning of the process. And you'd be surprised how many designers can spot mistakes they've made in the design just by looking at the fab sim. It's often the case that they'll revise the design even before the first board is built. Now, all the data collected at feature extraction from the design and the BOM and the fabrication simulation, everything our system has learned about materials and tolerances, everything it's learned over the thousands of other boards we've built over the years, and any last-minute design changes submitted by the customer, all of it is represented in the digital thread. Our software adds to that everything it knows about the other jobs being produced in the factory that day. It optimizes the start times and builds based on inventory and shift changes. Even things like the ambient temperature and humidity in the factory that can impact production are included. And then the factory does something remarkable. It programs itself. Each production line is comprised of at least 6 robots, each performing a different function in the assembly of a printed circuit board, from placing tiny chips on boards with pinpoint accuracy to scanning finished boards for any defects. Now, we use third-party robots that many other contract manufacturers use. In those other factories, as I said, people spend 2 to 3 hours programming each one for the next job, taking time out between builds and using information that was imperfectly gathered and subject to error. But at Tempo, we've worked with the makers of those robots to obtain access to low-level programming interfaces or APIs. Rather than having people sitting for hours at screens programming each machine before each job, our digital thread programs all of the machines in minutes. Our software also uses access to those low-level APIs to allow the machines to report out information on what they're doing and how well things are going. The robots are always chattering, delivering information to our secure private cloud that reports on progress, as well as any problems that might arise. Aware of that information, the factory can adjust on the fly to account for any problems and their resolution. All of that data serves another purpose. We share it back to our customers through a real-time dashboard. the Tempo order tracker. Our customers at any given moment can see exactly where their order is in the factory, when the build started and when it's due to complete, from order submission all the way through to the delivery of the finished boards. If you've ever used the Domino pizza tracker, this should look familiar to you. In a very real way, we use our software to place the factory in the hands of our customers. Our goal is to remove the barrier between the designer and the production process that builds their boards. Our software-driven smart factory hands the control to the person closest to the original idea and intent. The Tempo Smart Factory is not like the factory that built the laptop you're sitting in front of or the phone you hold in your hand. The factories that mass produce electronics are set up once to produce hundreds of thousands or millions of copies of a single thing. They're tooled and programmed to spend uninterrupted months building the same components over and over again. The Tempo factory is different. We work in a high mix, low volume environment. That makes things a lot more interesting. A single production line at Tempo might start the day building electronics for a heart monitor. An hour later, it might be building boards that will be launched into orbit on communication satellites. Before lunch, it might be building systems for 100 prototypes of an autonomous vehicle. Later in the day, it's parts for industrial robots, jet aircraft, wearable glucose monitors, or something else completely different. Multiply that continuously changing mix of products over many individual production lines in our factory, and you'll see the benefit of the software and automation we've built. It's years beyond what anyone else in our industry is doing. If you'd like more info on what we're doing at Tempo, please contact me. And someday when this pandemic is over, I'd be delighted to give you a tour of our smart factory. Thanks, and I'm open to any questions you might have.
Thank you very much, Brady. Here we go. Okay, everybody's seeing the two of us. Very interesting discussion, on what the future of the smart factory looks like. You gave some examples of customers and ways that you are working. How much of this is actually real today?
It's real now. We began the process of developing the software and building the first iteration of the factory back in 2013. And we've moved through successive iterations of the software, improving it at every step, and moving from what was a very small factory that was located actually in the hallway of a building in the Mission through successively larger factories to the one we're in now, which is in Potrero Hill and comprises 43,000 square feet of operating area. But as I said, we're not done. There's a lot more we'd like to do. Much of the process is completely automated, but there are still some parts that rely on human intervention and machine-aided work. The more of that we can actually automate, the better. I should say, by the way, we'll never be a lights-out factory. We need people. The difference between our factory and others is that in other factories, people are the machines. In our factory, people manage the machines.
That's a great way to put it, because yeah, I've definitely seen some interesting documentaries over the last year around the other way, around people are the machines. In terms of the data, you're dealing with a lot of proprietary, confidential data that your customers are providing. I heard you say private cloud, but how else are you protecting it?
So our customers do entrust us with an enormous amount of very precious information that describes the technology and the satellites they're launching and the medical equipment they launch into a very competitive market space, autonomous vehicles, and the rest of it. Our job is to protect that. So our factory is ITAR registered. That's a particular government registration that denominates the processes by which information is safeguarded. We also use, for the submission and storage of that data, the Amazon GovCloud. It's a hyper secure facility that even the government's three-letter agencies use. And inside the factory, the communications between the Amazon Gov Cloud and our own internal private cloud, all of that is deeply safeguarded and encrypted so that it never leaks outside the factory. But that information is useful to us. Again, it informs every aspect of the process. And we take everything we learn from every build to get better with the next build we do. The system is continuously learning.
Interesting. And, as the customers kind of start doing this and kind of controlling the factories themselves, you said, that they can do that even if they're not, I would say, technical. Is it too complex for non-specialists to run this, or can anybody do this?
A good analogy is the printer, right? In the old days, you would devise a document and then ship it off to a printer who had an elaborate factory setup and then would do the typesetting and send back proofs, and you'd go back through several iterations, but you had to rely on the expertise of that printer to deliver the final product. Of course, now we all have incredibly accurate and colorful printers in our own house, and we simply click the print button to make it happen. Ultimately, something like that is our vision for the future. We'd like it to be the point at which the designer simply goes into the menu of their design program and selects a menu item called Build. And that alerts our factory that they're ready to build that product. The factory programs itself, orders the products, and the minute the last part arrives, begins the building of that product for the customer. That's possible. We're not there yet. We still exercise an enormous amount of proprietary technology and information that we have and experience on behalf of the customer. And that's likely to always be part of it. But the closer we can get to that analogy of the printer, we think the better electronics processing and building becomes.
Okay, that makes sense. We have a question from one of the attendees. What are the top 1 or 2 hiccups you encounter in the supply chain or the end-to-end process? And he's specifically asking mostly human-based reasons.
The long pole in the tent is always the hardest part to obtain. The minute we get the design in and we ingest it, do the feature extraction, the fab sim, and the software goes out and immediately begins ordering the parts. The production, however, can't start until that last part gets in the door. Now, our system is designed to order parts. If we get the order before mid-afternoon, we can order the parts and typically have them in the next day. But it can be the case that a part is so unusual that it may take an additional day or multiple days to receive it in our factory. So that's the long pole in the tent. In terms of the question about sort of the human interface and where things might go wrong, since most of the process is automated and the rest is sort of machine aided, we've done the things necessary to sort of avoid interpretation, and that is the single biggest problem in most factories. In fact, that digital thread I described organizes not just what the machines are doing, but it actually organizes the activity of the people that work in our factory. They carry around devices that carry what we call the digital traveler, and on it, it tells them all the jobs that are coming through the factory, the order they're coming through, the times they're programmed, and it directs their attention to parts of the factory where that's needed.
Understood. It looks like Talia is here, which means we are out of time. But I'd like to thank you, Brady, for a very interesting conversation on the factory of the future. I'm sure everybody who is sitting at their laptops and desktops are clapping right now. Thank you, everybody. Feel free to comment on the chat with any thoughts, and please continue to use the Q&A functionality for everybody. So once again, thank you very much, Brady. And
thank you.
Hope you enjoy the rest of the day.